Hello, and welcome to Regression Analysis in Python by me, Dr. Alan Brain. This course covers simple linear regression, multilinear regression, categorical variables in a multilinear regression, and logistic regression. This course does not cover the theory. The variable files are available at drbrainstats.com. As we are concentrating on the theory, we can drive straight into an example of simple linear regression. In the sale of new cars, it is generally the case that the more expensive the car, the greater the profit to the dealer. The sales manager wants to help the salespersons make the most profitable sales possible to each customer. One particular area of interest is the amount of credit successfully applied for new car purchases. The manager has obtained a sample of 30 recently completed car sales where the customer secured a credit loan. The dataset Reg01 contains two variables, x, the gross annual income of a purchaser in thousands, and y, the amount of credit loan obtained by the purchaser. It would be clearly helpful for a salesperson to know how much credit a potential purchaser can apply for, given the knowledge of their income. And this brings us to the solution. Rather than talk through code, which I know is boring, I'll just briefly describe the steps. First of all, we need to activate a new library and import the data. Second, we need to create our target. This is y, based on our data frame Reg01. Next stage involves creating data with a variable we want to use to predict y. The package data model in Python does not include an intercept in its results, unless a variable has been created. In this case, we have used this code. The same result can be achieved by just making a new column and let it equal 1 all the way down. The model is based on OLS, where it uses everything that is in X to predict Y. By using the code calling .fit, we obtain the variable results. And finally, we print out our results. And so we got our results. Python provides us with a lot of information, but we just want to solve y equals mx plus c. We can see from our results, predicted credit equals 3.436 plus 0.196 times salary. The t statistic tells us whether this variable satisfies the 5% rule. And as you can see from the results, it does. But how do we know if the model is any good? This brings us onto R squared. R squared is a measure of goodness of fit of a linear regression. The value R squared is a fraction between 0 and 1 and has no units. If you have an R squared below 0.7, we should question whether there is a relationship between the variables. So now we go back to our results. With an R squared greater than 0.7, we can use these results with confidence. So if someone asked us, how much credit should we give for someone whose salary is 30,000? As our data was in the thousands, we would need to amend our x value to 30. So solving it as shown tells us that the credit off it should be 9,300. Now we can start on multiple linear regression. It's a rare occurrence when we can use only one variable to predict an outcome with confidence. When we use more than one explanatory variable to predict the outcome, we call this multiple linear regression, where y is the intercept, c is the intercept, and p, xp are the independents or the explanatory variables, and e is the error term. When developing models, the error term value is very close to 0, so is ignored. This is only here for the equation accuracy and won't be considered further on. So how do we measure multiple linear regression? This time we have to use the adjusted R square. In multiple regression models, the R squared will increase as more variables are included in the model. This is an adjustment of the R squared that penalizes the addition of extraneous predictors to the model. So now we start on our first example of a multilinear regression. A CSV file called multi1 contains the values of the following variables for a sample of 19 companies. Our first example involves constructing a multiple linear regression model to predict PER from profit and growth. So first, our code solution. As before, we import the data, create our targets, set our variables, we create the model, and then we just print out results. The program is very similar to our simple linear regression code. The main difference is that our X data frame has two variables. These are the results. Using estimates, the multiple linear regression is as shown. As this equation uses two explanatory variables, we have to use adjusted R-square for its performance. With adjusted R-square of 0.54, we may need to consider using this model as it falls below the 0.7 mark. But if we lack an alternative model, then we'd have to use it. This brings us to our second example of a multilinear regression. A CSV file called multi2 contains the first order of drinks consumed in a restaurant or bar based on its first 31 days. We want to construct a multiple linear regression model to predict the drinks remaining from the average price of a drink, the drinks ordered, and the average daytime temperature. So as before, we will import our data, set our target, create our variables, add the constant, create the model, and produce our results. As this model has three explanatory variables, we use the adjusted R-square value, which is 0.68. With a value close to 0.7, we can consider using this model with confidence. If we look into results more closely, we notice for the variable x1, the average price of a drink, the t-statistic is greater than 0.05. Therefore, we need to consider dropping this variable and create a model without it, as shown on the slide. Now with our new model, we can see that the t-statistic has been satisfied and the adjusted R-squared has not dropped significantly. Sequential approaches. Variable selection techniques tend to cause arguments among data scientists and statisticians, which I will not delve into here. There are always people dismissing procedures no matter what field you're in. I only mention this so that you're aware of this argument. We have just constructed a backwards sequential approach. Which now brings us onto categorical variables in a regression model. Categorical variables can provide further insight into predicting outcomes, for example, customer gender or region. A CSV file called categ1 contains 19 companies with the following variables. Import this data and construct a multiple linear regression model to predict PER from profit, growth, and industry. Before we can go into the solution, this gives us a chance to introduce dummy variables. Dummy variables are independent variables which take the value of either 0 or 1. As an example, if you had a variable called children which had two values, yes or no, creating dummy values, this variable requires creating two new columns where each time it equals yes, be 1, and then the other one where we no, make this one equal 1. So in essence, for every being created, we will create that number of columns based on each value. Dummy variable trap. When creating the dummy variables, we need to be cautious of using all of the dummy variables created. If we included all dummy variables, then the model will suffer from multicollinearity, the dummy variable trap, as they will be highly created, as one of them can be predicted from the other. Using our children variable example, for every time children yes equals 1, children no equals 0, and vice versa. Therefore, we could use children yes to predict children no. To solve this issue, when we create our model, we exclude one of the dummy variables from each variable we wish to model. So for children, we could only include children yes. The dummy variable dropped is given a score of 0. And now we're on to our solution. Well, as before, we would import the data, but before setting our target, we will create our dummy variables. Then we proceed as before. And this is our results. With a categorical variable included, each bin has been given its own score. Unlike continuous variables, when we multiply the explanatory variable by the estimates, for categorical, they have a fixed value. The results gathered has shown us that profit is not a good explanatory variable to predict PER. This brings us to the next stage. As we know, profit is not predictive. We'll model again without this variable. But we can see now from the results, Industry 3 is also not predictive. Therefore, we will drop this and combine this with Industry 1. So now our 0 value bin is now Industry 1 and Industry 3. So these are our final results. So the same as before for code, but we're not modeling Industry 3. Now this time, growth has a t statistic greater than 0.05. So we may want to remove this as well. This is personal choice and it is only just slightly over 0.05. In this instance, we are not, and we'll just write up results as shown. Which now brings us on to logistic regression. Logistic regression is used to calculate the probability of an event occurring. For example, a person responding to a direct mail or a customer defaulting on a loan. When considering a logistic regression, we need to add up the model scores, then convert that score into a probability, as will be demonstrated. In this exercise, we'll be using a CSV file called Logistic1. So import this file and call the data frame Logistic1. This file has a binary response variable called sold, which is equal to 1 if a sale has been made and 0 otherwise. There are 3 predictive variables: income, mortgage percentage, and tier. The variable tier takes on the values 1 to 4. Tiers with the rank of 1 have the highest prestige, while those with 4 have the lowest. This is our solution. As we can see, the code looks very similar, where the only main difference is that we're using logit instead of OLS. And these are our results. We can treat the PZ values as did the PT. As we can see, all variables satisfy the 0.05 rule, and our equation is as shown. But we have to convert the score into a probability. So we're going to translate these results using ID1, which has a tier equals 3 as an example. We'll score up our model as we've done in a previous example, which gives us our score minus 1.568. Now to convert that into the probability, we apply it to the equation as shown. So therefore, the probability of a sale for ID1 is 17.26%. This brings us to the end of an introduction to regression techniques used in Python. Additional material is available in this reasonably priced book, available on Amazon.